Hello and welcome. I'm Bori Zhang from Tsinghua University. I'm glad to introduce our optimizer Bort, breaking the trade-off between accuracy and explainability. We have released our code on GitHub. The black box nature of deep learning hinders its wide application. Black box explanations only focus on the external behavior of the model. For in-depth understanding, we advocate white box explanations. There are two difficulties. One, most work rely on the descriptive definition of explainability rather than a mathematical one. Two, a rise in model explainability often leads to a decline in accuracy. In this work, we start with the mathematical definition of comprehensibility and invertibility, which are two aspects of explainability. Then we derive boundedness and orthogonality as sufficient conditions. Finally, we design Bort optimizer to optimize models with two constraints. Interestingly, Bort does not impact the model capacity that leads to the improvement in accuracy. Most FNs, such as CNs and abilities, can be unified under one metastructure, that is an MLP with optional non-parametric operations. For example, the convolution and transformer additionally use folding and self-attention operation. That we focus on the explainability of MLPs. We need to consider two aspects. One, model-centric. We deal with concept alignment for the process. The activation often works as indicator about similarity between weights and inputs. However, inner product actually does not consider with cosine similarity. We argue that the weights should look similar to a semantic pattern, which are defined as comprehensibility. Two, data-centric. To understand the hidden variables, we need to map them back to input space for better observations. Therefore, we define invertibility. MLP employs inner products to calculate activations. For comprehensibility, though X and V2 are more similar, V1 produces larger activation because of its larger amplitude. To align activation with cosine similarity, we only need to restrict all weights in a hypersphere as equation 1, which we name as boundedness. A number of approaches believe that the linear combination of weights can reconstruct input as equation 2. However, such reconstruction operation is not guaranteed. That we formulate an object to achieve the optimal reconstruction as equation 3 and derive the orthogonality condition. Subsequently, we attempt to combine the standard descent algorithm with bounded orthogonal conditions. The original form is equation 4. We found that the two conditions can be merged as one. We then rewrite to an unconstrained form by utilizing the Lagrangian multiplier. Finally, get Bort as equation 7. For convenience, we set all lambda I to be equal. We try to give an intuitive understanding about impacts on model capacity under a simple setting. Research about stochastic configuration networks revealed that scattering latent weights benefits the property of universal approximation. Rigorous proof of keeping model capacity in general cases will be our future direction. Bort can simultaneously boost performance and explainability. We test the Bort on MNIT, CFA10, and ImageNet with various models to compare with baselines such as SGD and MW. Table 1 and 2 show the consistent improvement in performance. To verify whether weights satisfy bounded orthogonal conditions, we show the distribution and reconstruction compared with SGD and observe a clear improvement. For qualitative visualization, we conduct a reconstruction and a salience analysis. Figure 4 shows the reconstruction results with guided BP, and Figure 5 shows the salience maps. All visualizations demonstrate that Bort boosts model explainability. For quantitative analysis, we compute deletion insertion metrics. In most cases, Bort significantly surpasses counterparts. Moreover, we explore what Bort can provide for an in-depth understanding for networks through feature decomposition and sample synthesis. Figure 6b shows CNN multiplied by Bort is compositional. In Figure 6c, we can synthesize adversarial samples by manipulating spatial features in MNIST. Readers can get more details in our paper. In this work, we first derive boundedness and orthogonality with mathematical definitions. Then we design the Bort optimizer. Reconstruction and the salience maps shows a clear improvement of explainability. Last but not least, Bort also keeps consistent improvement of accuracy, which breaks the trade-off between performance and explainability. Welcome to see other works in your group, and look forward to further discussion. That's all. Thanks.